Okay, let me share my screen. Okay, great. Are you able to see my screen?
Yes, it's shown.
Yes,
Ah,
yes, we can
okay.
see it.
Yeah, so basically this is the still the same presentation that I had for DARPA, so I was just using the same one. Yeah, as Meena introduced, so the name of this research is Interpretable Multi-Head Self-Attention Architecture for Sarcasm Detection in Social Media. So one of the big projects that we have had in our labs is Social Sim project. It's funded by DARPA. In fact, Steve was also on the project when he was working with us in the lab. So the main goal of the project is it's kind of having a computational like a simulation of a human behavior, how they interact and what kind of behaviors people like show when they interact, and what kind of these behaviors would lead to all sorts of this extremism or all kinds of behaviors that we see. So that's the main goal of it. But my research is like funded by DARPA, but not directly for the challenge of the DARPA. We were looking at what are the other tasks that we can accomplish in the social media space using machine learning techniques. So one of the initial thoughts was like understanding the language itself, so how people communicate. And within the language, we notice that there are like different fashions, like different styles, like being ironic or being sarcastic, um, and sometimes also being toxic. So what is this like kind of toxic languages? How do people like I mean, what motivates them and those kind of things. So in that route, our first step was to start with the sarcasm detection. And right now so after this, once this was done, then we started looking at also the toxic span detection and the toxic language detection. So the work is almost done. So we'll be like doing a paper there. So this one was like the earlier one. Actually, this was finished in 2019, but it took quite some time for us to get the publication out. And yeah. Um, Anyway, so this one is mainly looking at the sarcasm in the social media. So why it is essential, as I said, so when people express their emotions, sometimes it's positive, sometimes it's funny, and sometimes this figurative language can be negative, and it also impacts like the other people's emotions. The way we define it is, and the definition we put in the paper is an assortment of mockery or false politeness to intensify the hostility without explicitly doing so. So, in our face to face conversations based on the mannerisms or the behaviors or the gestures, it's easy for us to understand how the other person is interacting with us, is he being sarcastic or not, and at what level. So the severity also matters. But when you're in a social media, you really don't know. I mean, of course, like the people that you know, it's easy to understand. But let's say if you're talking to someone, or if you're following a tweet thread started by somebody, so you only know them by their profile or so, but not really as a human, like one to one. So in those kind of situations, it's very hard. And what we've noticed is that this kind of figurative language that used in the social media also helping propagate the misinformation camps. We did see that trend in some of the data sets, like some of the data points in Twitter. Yeah, so that's another parallel track that's going on right now. But yeah, so sarcasm can also lead to all this unwanted stuff, like as I said, like the misinformation or the disinformation propagation that happens on social media, which eventually leads to extremism, in some cases. So and not just that, and also this helps in identifying like the cyber police and the online trolls, which is also like, and it's a part of the sentiment analysis. So earlier people used to look at only if the given statement is has a positive sentiment or negative sentiment, but a level above is actually to detect at what level it is negative or at what level it is positive. So that's what this work is about. So in this work, we used different encoding techniques. So the first point that I used is the BERT model, but actually we did use the other embeddings. As we all know, so we need the data. Data is the most essential thing for the machine learning part, and so we take the real data and then convert it into numbers and then feed it into the network. So that's very common. And this process is called the embeddings. And so we have the pre-trained models that are trained on millions of data sets. And one of the latest ones is this bidirectional encoded representation from transformers. So we just used this embedding. Also, when I talk about the ablations, I'll talk about what other embeddings that we've used for different experiments. So mainly we use the BERT. And then we have this main block, that's the architecture block, which has the self-attention module, which I'll talk about it in a minute. And then we have the GRU unit to understand the long range relationships between two words in a sentence. If you have a sentence, how do you know the relationship between one word to the other word if they are like quite far away from each other? And then we have the classification classification task followed by the probability score. So that's the overall picture of the architecture that we have. One of the main things that stands out from the previous works is that we also incorporated the interpretability part of this architecture, because we all know that machine learning is a black box model. We don't know what it is learning or why it is learning, and so on and on. And of course, there is a big debate that's going on about how do you define the explainability? I mean, how do you have this concepts of explainability or interpretability to support what your algorithm is talking about, or what your algorithm is learning, and so on. That's a different field, but then yeah. So for us in this research, we use this the attention scores, and then we try to visualize it based on the heat map or the range it gives. We would we would know why it is giving certain attention score for individual words, and why is like the emphasis on a word and why there is no emphasis on another word. So this is basically through the kind of a heat map visualization that we have there. That helps us understand why this model is classifying a certain text as sarcastic or not sarcastic. Then, yeah, of course, we have the state-of-the-art results on multiple data sets. And also we did the extensive experimentations and the ablation studies that Meena just told, and that's true. And then we also have this attention analysis and the failure cases. Yeah, so attention mechanism, it's kind of like it got quite attention topic got quite a bit of attention in the NLP community lately, mainly in the field. Like it started with the machine translation. It's kind of having how do you have a different so the basics is that it has the key value and the query. So when you have different projections of the same input, and when you combine them, or when you have some kind of multiplication or an addition, what is the benefit that's coming out of it? So what is the computation effort combining the different input projections. And that's the overall, like in a nutshell, it's a attention mechanism, and it's been there in the field since 2017. So we kind of use the same method, and this is the overall architecture for this task. So starting from the left, we have the input text, and we convert the input text to the word embeddings. And then in this work we have different word embeddings, and then the main work is the purple color big block that you see there, which is actually taking, it's actually uh, it's multiple head across multiple layers. So that's like a pretty like kind of a pretty big architecture to visualize. um, and in each of these heads, we would take different projections and have a product of those, and then we compute the attention scores, and we continue to do that across multiple heads, and then and for each layer across multiple layers. So we have different projections across multiple heads and across multiple layers. So yeah, that gives us that actually takes all sorts of possible combinations or the patterns within the input in order to get those attentions. Yeah, so and the map that you, or the colored checks that you see there, those are basically the attention scores, the representation of the attention map. So what this attention map does is, when it computes all the probable projections of the input, and it computes the score, and then it gives the score. The color is represented by the score, and like symbolically we use the map just to say that, okay, this is an attention map, which is combination of all possible attention scores for all the input projections. And in the output from this architecture is further passed to a GRU unit. So at this point, it's just, I mean, we can run this experiment. We did run the experiment without the GRU, and with the GRU, there is not much. To be honest, there is not much of a difference as far as I remember, but we just let it there because I mean, it did not harm or it did not know any benefit. But usually the reason why we use GRUs is that when we have like big sentences, how do, based on the context, how do you connect one word and then the corresponding word in the following sentence, that's pretty far. So having those connections and having those kind of contextual similarities, that's the main reason why we use GRUs. And then the input is then further passed to a fully connected layer, and then it's just the end gives a probability score, because it's basically a classification task. Given a sentence, we just classify whether it is sarcastic or not, and the probability score is the one between the 0 and the 1. So any model can predict 0.5. So the model is said to do well when it is predicting anything over or close to 1, and it does really bad, or it does really good in not classifying when it is close to 0. So yeah, I will show those results in a minute. Yeah, these are the data sets that we've used for this particular task. These are pretty much like well-used data sets for this task in the field. Two from Twitter, and one from the Reddit, and one from the headlines like the HuffPost News. And then we have the dialogues data set as well. Yeah, so the interpretability part that I was talking about. So this is, I don't know if you can read this. It's readable for me, but I don't know if it is clear enough, but I can explain. So what it does is, so just focus on the upper rectangle. In the upper rectangle, it shows how the attention scores change from first layer to the fourth layer. So How do we set these layers is basically empirical analysis. We do a number of experiments, and then we, based on the results that we get, and then we put a threshold. Okay, in this case we take like 5 layers. So 5 layers is where we stopped, because then it would start overfitting the data, and then the results would kind of show downhill trend. That's a very common way of like picking your upper bound. Yeah, so we have 5 layers, and the index starts with 0. So the layer 0 to layer 4 is the upper triangle, that shows the attention analysis with the sentence that has sarcasm in it. And every word is connected, every word is kind of not connected. Connected is the wrong term here. Every word is compared against every other word in the same sentence. So if you see in the layer 0, the first column and the second column, they are just the same sentences, and every word is like compared against it. And the CLS on top and SEP at the bottom, those are kind of identifying tokens. CLS stands for the classification, SCP stands for the separation. So these are kind of a standard tokens to differentiate different sentences. So whenever there's a CLS, that means it's the beginning of the sentence. SCP is the end of the sentence, and then followed by the rest of the sentences. Yeah, so those are identifiers. And from this the upper triangle, we can clearly see how the attention scores, when it is computed using this self attention, the multi-head self attention module, which I told you about, like being very complex inside to visualize. When all those computation is done, then the emphasis changes. So like for example, you can see in the layer 0, just segregation totally, and the exclamation is given a higher priority, or higher emphasis. But when we go to the next layer, after again a bunch of iterations within that module, then it changes to totally an exclamation, and then so on again. In the layer 2 it's different. But when we come to layer 3 and 4, it again starts to like kind of a saturate. So everything is connected to everything else, and you don't really see a pattern there. It's just one sentence that we have picked, but we can see that so at a sentence level, we can think that okay, training must have stopped at layer 2, but then this is only for this sentence. But we have so many other data sets, or actually so many sentences within each data set. So we take the overall analysis, like the overall emphasis and the overall attentions and attention score computation. And then when we look at the F1 measure, is basically the harmonic mean of the sensitivity and the specificity. So we look at when the F1 measure is starts to deteriorate, like it will raise to a point, and then at that point at some point it will start to fall, and then that's when we will just stop training, or we'll just stop there and give it as an upper bound. So the upper bound decision should never be done on a sentence level, but on the entire data set or the entire model level. Yeah, similarly, the second figure is also the same, but this one is mainly the sentence without sarcasm. So these are the data sets that we've used are actually annotated data sets. Like for example, the Reddit data set, they always have a /s sign that says, so when I post something on the Reddit and I put /s, it's understood that it's sarcasm. So there are I think the people who actually gathered collected this data sets, they've used different techniques, and also they considered the user input using this kind of clues, like a /s, or for example hash sarcasm, in Twitter and these kind of clues to annotate the data. So we just took the data sets that are like pretty well used in the field in this research area, and then we just applied here. I mean, we just used it for this research. Um, One other thing is that there is also another like a parallel discussion that's going on that says that humans are really not well in detecting sarcasm. So whoever annotated the data probably may not, or even the users, like as a user, probably they also not know what they're annotating. I mean, that's all. There is always like a contradictory parallel discussions that happen. But yeah, for this research, we just use the data sets that are already there. Um, yeah. Um, so yeah, this is one way of visualizing when you want to look at the entire analysis or the entire visualization of how the attention scores evolved from first layer to the nth layer, in this case, layer number 5. Um, but this is the entire head, like the when you remember I talked about the each heads and then across each layers. So we saw the layer part, and this is the head part. So here, so the rows are like the different layers. That's what we see here in the previous, oops, yeah, the previous slides are the layers. So this the first blue color ones, those are the individual layers, and then the columns correspond individual heads in the layer. We tried our best to visualize this because it's I mean, for human to understand what it is, it's and because it's a multidimensional network, and then we have to bring it down to 2D way. Yeah, so we just thought probably this would be the most efficient way to do it. Here also we can see how the attention scores um, change over time across individual layers and across multiple heads. So the if you look at the third row and the second column, it is basically the layer 2 and head 1. But I say it's a third row and second column because our index always starts with 0. So that's why it's layer 2 and head 1. And that is the one in the white color is basically to show how the each individual words and how the attention scores, just like the visualization that we've seen in the previous slide. It's the same that we see on top here. Yeah, this is an example for the sentence with the sarcasm to show how the attention score starts to like change over time. And then like for example, in this case, after head 4, oh no, after head 0, 1, 2, 3. Okay. After head 2, it starts to just saturate. And then also with the layer wise, if you see within the second layer and the head 5, it just starts to saturate. It's a yeah, it's also a similar visualization, but this is more for the sentence without sarcasm. Some sentences are really long, but it's just the mechanisms is still the same. So there is no limit on how many number of words would fit in a sentence. We would just take the input as it is, as like in case if a user has no, not a user, because we are using the annotated data. So each sentence is like, let's say it has 10 words or 15 words or 20 words, we just take it as it is, and we always use the CLS and SAP to separate between two sentences, and the mechanism is still the same in between. Then this is a third visualization technique to show the attention analysis. So the the left side columns are the sentences for the sarcastic and non-sarcastic, and the right side column is basically the prediction score. After all the computation that's happened, and then the end score that we get is basically the prediction. Mm, And the color changes that you can see for each individual sentence is basically the heat map. If you can see the difference of different um, red colors, and it's the composition of the word, and the change in the color is basically the attention score that it is computed. So based on the score, the color changes. The thicker it is, the thicker it is, the more emphasis is given to the word. For example, the first sentence, after all the computation is done, it predicted hash hash a totally, first and ever. So these are the most contributing factors to predict that sentence as sarcastic. I mean, I as a human understand English, but if I have to do that, it's very hard without a context, because I don't know what they're talking about, what this sentence is about. So that is when the machine learning would help. So machine learning can work and in terms of the content and the context, and with all the computation that happens, and then it gives this prediction score. Some sentences, it is easy for us to like easy for us to understand. Okay, this could be the reason why it predicted. But some sentences, as I just said, I have no clue why it predicted like that. But when we look at the different attention scores, then it makes complete sense. Okay, this is why it is working for different sentences. And then it gives a different probability score, sorry, different attention scores, and then it gives a probability score. Because I have no clue for the context. But the machine learning algorithms, it does well when it even does not have context. Yeah, these are the results for the data sets that we've used. From so all the uh, so whenever I say our model, that's the interpretability model that I was talking about, and the rest all are just the previous methods. And the numbers here, like the 1440 and 2420, are actually the references that we've used in the paper. Yeah, so we have those references in the paper, and those are the models from their scores. Um, from this slide, if you look at any data set, our model did really well in comparison to the previous models. Well, anyone can just say, well, it's just a difference of 1% or just 2%. But in a machine learning community, probably you all know by now, it's a really difficult space. Like people fight even for like 0.1 0.2% of improvement, and there's like really big conferences that people present, like a NeurIPS and CVPR, like the computer vision and the pattern recognition conferences. These are very sophisticated conferences, but then even in those conferences, we can clearly see that having at least like a 0.5% also like plays a big role in having their papers accepted and so on. Yeah, so in general, yeah, we can see it's a quite a bit of a improvement over the state of the art across multiple data sets that we've used. Um, yeah, so these are the ablation studies. So the first ablations is that we changed the number of layers, and we put the constant number of heads. Like the heads are always 8, and we just use changing the layers, and we saw that after third layer and probably like 5 layers, it just remained there, and then it started to go bad, and then we stopped it there. And similarly, the next ablation is now keeping the layers constant, and then we change the heads. um, and the third ablation study that is the one that I was talking about, the embeddings. So embeddings is the one where we convert the English sentence into vectors, the process of converting and then using that vectors as an input to the algorithm. So there are like the algorithms that does that. So these embeddings We've used the BERT as our first step because when we started in 2018, that was the one of the promised model, embedding model. But then we also like trained on using the Elmo Fastnet for Fastex glove with only 6 billion parameters, and then a glove with 840 billion parameters. So in all using this embeddings, yeah, so the reason why we did that is when we started with the BERT, because at that time BERT was doing really well, and we thought maybe BERT is contributing also to the results. So to check that, then we thought using the other embeddings, and we clearly see that BERT did not actually contribute much rather than what it actually does. I mean, it did not change the actual computation internally. It did not carry any of it, but um, it just helped with using the embeddings itself. Yeah, and when we worked with the different embeddings, we can clearly see that our F1 score stayed pretty much in the same range between 75 to 77. It just like a little bit change here and there, but not really any contribution from the embedding types itself. Um, yeah, so that's pretty much about this work. So yeah, we have mainly this architecture has like 4 different components. As I said, first is the pre-processing using multiple embedding techniques, and then we have this giant multi-head self-attention module which we try to visualize in a small block. But no, I mean, if you can visualize, it's really like really huge, because having these different projections computed across multiple layers, and for each layer then the multiple heads. So yeah, and then we have the GRU unit. So as I mentioned earlier, so having a GRU or without a GRU, it just stayed the same. It did not impact much. And then yeah, we have the classification module, which is the after it just computation is done, then we have this fully connected layer, which actually does the classification to get the probability score. And the another novelty part about this work is the interpretability part that I tried explaining using different visualization that we have for different layers and the layers and the heads, and then within the each individual sentence analytics. Um, yeah, and we have the experiments that we've run across multiple data sets and the ablation studies, and we got pretty good results across all these experiments, and it did help the community, and I'm happy about it. So one other thing is that we DAPA really liked our work, but I'm not sure like how the proceedings would be, like DAPA adapting this technology in order to have like have it really there. But yeah, that's a different part, but I definitely see that Tapa was like really interested in this work, and that's how actually why the media like we got so much media attention for this research. um, we definitely see there is a lot of potential there to help the community, not just the research community, but from a daily, like like a daily application standpoint. um, yeah, that's pretty much about this research.
Thank you, Ramya, for the presentation. Really interesting stuff. Uh, I don't know if anyone has any questions. I have a couple. So if no one has questions, maybe I
I
can.
I have a simple one.
Yeah.
When you like train, like when you actually like train the model, are you uh evaluating it like just that sentence, or do you keep any context from the thread or previous
Context?
statements?
Yeah, so no, no, we are only using the sentences only, and there is no other additional information, additional input given to the network. So that's why I gave you an example of this one, where like for me as a human, if I see I don't understand anything because I have no context or I have no clue why, I mean, anyone would predict as a sarcastic or not sarcastic. But that's when we humans cannot decide on certain things, that's when the machine learning can help us. Yeah, so there is no contextual information given on top. It's just the initial embeddings that is the key input, and the main goal is having these different projections and the computation that helps us predict this.
I see. Could we go to the ablation studies?
Yeah.
I'm just wondering, like with the table 8 over there, it still seems like it's still going up. Did you try increasing the heads further?
We did. Yes, yeah. It's all part of the experiments. Yes, we did, and that's when we start to. I mean, that's when it started to deteriorate, and then we stopped it. Yeah. So all the like the layers, the upper limit on the layers and the upper limit on the heads are mainly through experimentation. Yeah.
Got it. And then I guess since this like study kind of concluded in 2019, but the paper just got out in 2021, if I'm right. Like,
Yeah.
are there any advancements in NLP that you would like, if you did this again, you would try to apply?
Um, so right now we have another work that's almost like we are looking at the last phase of the work. It's mainly, as I mentioned, the toxicity language detection. So the toxic language, for that we just train the models based on I mean, we have the data sets that are labeled, but then we are trying to not just classify whether the given statement is toxic or not, but we are looking at the spans of the toxicity. So what are the contributing factors? Like sometimes people use foul language or foul hashtags and those kind of clues. I mean, those kind of things. But yeah, so we have those span detection that's going on right now. That's where we are headed. Uh, Other than that, we have some other plans, but right now it's just we didn't start anything yet. Yeah.
Got it. Thank you.
So I was wondering how long did it take you to do all of these experiments?
I think we started in 2018 February, and I think it took like about 6 months.
Okay.
Yeah, so because mainly also like one of the big difference between the academics and the industry is the computational power. So we had to like go on and off. We have like a few GPUs in our lab, and then we were also using some university research computational credits and so on. But again, it's the experiments in machine learning. They really take a lot of time. So that's what I was explaining, like beginning of the session, is that so it's okay in academics to like when something fails, then you can restart and then tweak it and fix things and then run it again. But in industry, because time is money, it's like you cannot do so many experiments unless like you're in the R&D field, yeah, trying to get the state of the art model. Yeah, so that's why it took like 6 months for us. Yeah.
Okay. And I also have a question about one of the examples, I believe in slide 11. And I think my question is about the annotation process. I don't know if you have any information about how the different sentences or different tweets are treated. But the second sentence in the sarcastic group, I get why it's being like why whoever annotated it thought of it as sarcastic, but I can also see it as being non-sarcastic. Like someone might
Yeah,
say a similar sentence and just believe it.
right. Right, that's
So,
true. Yeah, that's what I was talking about. So, yeah, so when we do not know the context, so it's hard for us to predict. That's why there is a panel discussion group that's going on that even humans are really bad at like detecting sarcasm. Then that's when the machine learning algorithms would actually help, because we have no. In this particular example that you're talking about, yes, we as a normal users, we have no context, and to be honest, we don't even know like from which data set it came from and what was the previous thread or what was the topic they are talking about. Yeah, so when there is no context, then the algorithm helps.
so is there any way, of which we can use to measure how good or bad humans are at evaluating sarcasm? I mean, if we can measure how humans perform on this task, then we can compare their performance to the models and then determine whether the models are performing better or worse, instead of just saying that this model is good for detecting something that is inherently hard to detect. So, do you know of any such techniques?
I don't know if I understood your question right. So are you asking like if we can, I mean, if the algorithm helps human to detect sarcasm
Uh,
or?
I can rephrase it. So, when sometimes when the problem is even hard for humans,
Mhm,
such as this example, for
mhm,
instance, instead of just relying on how the model performs, like using the accuracy, for example,
mhm.
we can also compare it to how the humans are performing, and that's when we can say, okay, the model is performing better than humans. Just to put it into
Oh,
context, that we're
oh,
not saying that this model is perfect, but for this particular task, it is performing better than humans.
oh, I see, I see. Um, so as far as I know, and there are like when we have the annotations, that's when we have all these Amazon to mechanical turks and the humans, and then they try to look at the automatically annotated data and then compare it against the human annotated data to come into consensus. I know there's a work that are done by the algorithms and then humans and then the comparisons, but not for these kind of tasks, because this falls under the category of the like the pattern recognition tasks. So they like it's pretty I mean, there are like many studies in psychology where it shows that people are like, we humans are like really bad on at many levels in recognizing different kinds of patterns and then also like different kinds of things. So when in that kind of circumstances is where the ML would really help, and this example is one such. But otherwise, yeah, what you're saying, I did see some in the annotating the data sets.
Okay, I can think of like if one of the sentences is just like had different opinions. When it, Let me start over. So you talked about using consensus to determine the class of each sentence in the data set. So for instance, if a data set is unanimously classified as sarcastic, then we're more confident. If another sentence has a split decision going on, then we're less confident about it. So maybe this can be tweaked and used as a measure for how good or bad humans are at detecting certain types of sarcasm. Just this is just a thought on my behalf, on my part. So I have another question about maybe slide 9 or 8.
Yeah, so just one point before we do that. Also, so the reason when we humans do that, there are also multiple other factors that we need to consider, because we are like, we are humans, right? So we have so many emotions and so on, and we cannot just work like robots. And the other thing is the cultural differences and the cultural biases.
Right,
So
right.
sometimes, so what is okay in my culture may not be okay in someone's culture, and then when also the same applies for the severity. So it might be too funny or too okay for me that I go extreme, but it might not be okay for the other person. So there's always like the like the borders, boundaries, and these kind of stuff. That's when like the ML would really help across all these things. Yeah. Sorry. So which slide are you asking me to go to?
Maybe slide 9 or 8.
This one?
8, slide 8. Yeah. So in the second sentence, you say that sample sentence without sarcasm.
Mhm.
So I'm not really sure I understand what that means. So is this a
So
sample?
it's a sample from the non-sarcastic class, because
Oh,
it's a created data set. So each sentence is classified either sarcastic or non-sarcastic. There are two classes, and this
okay.
sentence comes from the second class.
So this is from based on the model's prediction. Like the model predicted this sentence as a non-sarcastic sentence.
No.
That's the okay. That's the
Data
original.
itself, the data.
Ah,
Each
okay. That's
data
the
class.
original class. Okay, okay.
Right.
Because I can also see this being used as like someone stating the obvious might be
Yeah, right.
a sarcasm technique. So
Yeah.
yeah. Okay. Got it.
I mean, it's just really special because there isn't a fish called a. Well, no, never mind.
Ah, yeah.
I forgot about dolphin fish for a second.
Right. Yeah, but that was a good clarification because I was trying to picture this kind of an unsupervised, learning methodology. But you're saying that there's already a set that is classified, and you're taking that then, to use it, to classify the other unknowns, right? The other
Yeah.
sentences. Okay, yeah. Now it makes a little bit more sense because I was saying, okay, but how can you then classify sarcasm if you don't have the context, right? The context is very important, at least in the human, in the human classification of how humans classify things. But then, yeah, now it makes a lot of sense now, that you have already, a data set that you have classified, okay, these sentences are sarcasm, these are not. And then you are using that model then to apply to the other data sets, right?
Yeah, just one thing. Though
Okay.
I did not classify these. We've just used the data sets that are already labeled. So yeah, which are
Right.
given the labels, but these are from the previous works.
Okay.
We don't do any data part, so we just took the data from these previous works.
Right.
Yeah.
But they have some, some targets there.
Right.
They have targets.
Yes.
Yeah. Okay. Excellent. Yeah. Now it's making much more sense now. Yeah. Yeah. It's like in the images, right? That you get, like, let's say 1,000 images that are classified as, let's say, cat and dogs. And then you bring other images and then you train the model to say, okay, if it appears to be like a cat, then classify as a cat. If it's a dog, and then you start trying to get the nuances of each of those, because there could be one image that is combining cats and dogs. Where are you going? Where are you going, right? But at least you have that baseline that then you can go on to classifying
Yeah,
the
that's
nodes.
all the pattern matching. Yeah, the pattern.
Right.
Stuff, right.
Now I mean it's very clear now. It's very clear.
We had a talk earlier this year about something a little bit similar to what you would to this. It wasn't sarcasm detection. It was another NLP implementation, and the team. So the speaker was from Purdue, and her team built a model that modeled context through other features. Like they collected information about the users themselves, if I remember correctly, and that kind of told them something about this whoever is talking or whoever is tweeting, and using that information, it kind of helped them have better results. So I think in this instance, it might something, some.
Yeah, and it was more, geared toward identifying political choices, political bias.
Yeah, right.
You're okay. So, for example, if someone is talking about, let's say, a lot about religion, about guns, etc., so that probably, tends to be on the right side of the spectrum, right?
Mm-hmm.
If you're talking about, I don't know, welfare, kind of socialist ideas, then you go a little bit to the left.
Mm-hmm.
Yeah, and it was very, very interesting, very, very interesting. Yeah.
Yeah.
Can I see the interpretability plots in slide 9 and 10?
Uh-huh.
Hmm.
Yeah.
Is the background the same plot between 9 and 10?
Yeah, it's
Oh
just
no,
a
it's
dark. It's a no. It's just a dark background, but then you see the layers change. Because in this one, the number of words within a sentence, it's a small sentence because it has
got,
number of less words. But this
got
thing is a little longer sentence, so yeah, I just try
yeah.
to get the visualization as much possible into the slide, so probably just make the dimension differences.
I'm a bit confused, like interpreting this, because like this is a sentence without sarcasm, but I thought that like an indication that it has sarcasm is if the weights are uneven, right? And you see those in the first 3 rows.
So yeah, okay. So just to make it clear, and so the here we have multiple layers and the rows. So the rows that we see are the layers, and the columns that we see are the heads. So when you want to look at like visualize it per layer, this is the best visualization. That's why I've been like telling it's just so complex for human to like kind of visualize such a complex thing, because we are trying to get these like different projections of the same input across multiple layers and the multiple heads. So for one time it's really hard for us to like get our like
Oh,
wrap our mind around it, but it just takes time. But when you look at the individual layer, so as I said, so we compute the attention scores for individual words, and we can see how that score is changing after the computation across multiple layers. In this case, it started with layer 0 to 04. That's a transition. And the same, if you look at it, the same transition, the changes, it happens across not just the layer for one head, that's the row, but also the multiple heads, it's the different columns. So it's like all sorts of possibilities, basically.
oh, okay. So it's not, you can't immediately look at the black
No,
image.
no, it's not. No,
Okay.
it's not. It's not. It's
Okay.
not.
Yeah.
Yeah, it's hard for a human visualization. Like if you could interpret just looking at this 2D image, no, it's not, because there is like it's a multidimensional network that we try to compress it to 2D, but there's a lot going on behind.
Got it. Was there like any like particular words that stood out that were like strong indicators of sarcasm, or is it not applicable to do such a
Um,
analysis?
No, in this data, actually, the beauty of these data sets is that I think they really filtered out like when they're working on cleaning up the data, they really filtered out the most of the unwanted stuff, or like the most obvious things. Like, for example,
Mhm.
when people use like foul language or the toxic language, it can always be like kind of a clue that could contribute to sarcasm in this context. But there are no obvious like kind of any toxic language, at least that I have seen. Like I did manually look at some of the samples from both the classes, but nothing stood out as such.
Okay.
So it's 4 o'clock right now. If no one else has any questions, we can end it here.
Yeah.